Every day, more than 100 million bullets are fired around the world. To meet this incredible demand, ammunition factories work around the clock, producing over 50 million bullets per day to supply the vast arsenals stockpiled by armies, police forces, and armed civilians. But have you ever wondered how bullets are made? Well, today we're traveling to the United States, home to one of the largest ammunition factories in the world, where over 250,000 bullets are produced every hour. There, we'll see each step of the process, from forming the brass casing and loading the powder, to inserting the projectile and conducting the final firing tests. So get ready, because today we're going to discover how bullets are mass-produced. Let's get started. Step 1. Selection of materials and components. A bullet consists of 4 essential parts: the casing, the primer, the powder, and the projectile. Each component plays a key role and is made from materials designed to withstand extremely high pressures and temperatures. The casing is the metallic shell that contains everything. It's mainly made of brass, an alloy of copper and zinc that combines strength with ease of shaping. At its base is inserted the primer, a small detonator that ignites when struck by the firearm's firing pin. Inside the casing lies the powder, a chemical compound that, when ignited, creates a controlled explosion that propels the projectile, the part that is actually fired. The projectile itself has a lead core coated in copper and can reach speeds exceeding 1,200 kilometers per hour, with the force and precision needed to fulfill its purpose. Each of these elements is produced under strict quality control and stored in secure conditions before entering the production line. Once all materials are ready, it's time to send them to the machines, synchronize the processes, and begin mass production of bullets. Let's go. Step 2. Casing manufacturing. The process begins with the production of casings. These are made from simple brass discs, a metal alloy that's durable yet easy to work with. Operators place the discs into massive automatic hydraulic presses capable of exerting up to 200 tons of pressure, shaping them into the proper form. First, the discs are drawn and stretched, then refined and formed with a base where the primer will later be inserted. Each stamped casing goes through a secondary machining process where a rotary stamping system engraves the serial number, caliber, and batch number. This information is essential for traceability, allowing every bullet to be tracked to its origin and helping forensic investigations if necessary. Once shaped, the casings undergo a cleaning process, being immersed in a special solution to remove metal residue and pressing marks, then dried with compressed air, leaving them perfectly clean and ready for the next step: powder loading. Step 3. Powder preparation. Now we arrive at one of the most impressive parts of the entire process: the production and handling of gunpowder. Everyone has heard of gunpowder, that grayish dust that explodes when ignited. But what exactly is it today? Modern ammunition no longer uses the same powder as centuries ago. It is stored in isolated areas, protected by sensors and trained personnel. Operators use high-precision metering systems that measure the amount of powder to be loaded into each case to the thousandth. The powder is then automatically metered through an adjustable nozzle, which deposits the exact amount into each case without producing spills or dangerous buildups. Once loaded, the powder is distributed within the case by gentle vibrations or pneumatic systems, ensuring it is perfectly seated before proceeding to the next step. When the case has been correctly loaded and checked, it's time to add the next essential component: the primer. Let's go. Step 4. Primer insertion. Now that the casing is loaded with powder, it's time to install a fundamental element: the primer. A small round piece inserted at the base of the casing. The primer contains a highly sensitive explosive compound that, when struck by the firing pin, produces a spark, like lighting a fuse in a movie, except it happens instantaneously. The most common material used inside the primer is lead stiffenate, a highly reactive compound chosen for its ability to detonate under minimal impact. Because of its sensitivity, handling this component is done under strictly controlled conditions with extreme caution. High-precision automated machines insert each primer into place, while operators continuously monitor proper operation and alignment. Optical sensors and cameras check that each primer is perfectly seated. Finally, the case is passed through a pressure test bench, which ensures that the primer is properly seated and ready to function without defects. With this component in place, the case is now complete. It contains the powder, the detonator, and only one final step remains to become a real bullet: inserting the projectile. Let's take a look. Step 5. Projectile manufacturing and insertion. With the casing charged and the primer installed, it's time for the star of the show, the projectile. Also called the bullet, it's the part that leaves the firearm and hits the target. To perform effectively, it requires a design that balances mass, stability, and penetration power. It all begins with melting lead in industrial furnaces at around 300 degrees Celsius until it becomes liquid. The molten lead is poured into small cylindrical molds to form cores for the projectiles. Next, these cores go through an extrusion machine that shapes them precisely according to the required caliber. For example, a 9mm bullet for handguns differs from a 5.56mm round used in assault rifles. The lead cores are then coated with copper in a special chemical bath that strengthens them without altering shape. This coating improves durability and reduces barrel friction during firing. Once ready, the projectiles are transported via automated conveyor belts to the assembly line, where high-precision presses insert them into the open casings, sealing everything perfectly. Operators inspect each connection, as even the slightest effect can affect trajectory or performance. Now the casing, powder, primer, and projectile are united into one complete cartridge, fully assembled and ready for testing. But before it can be deployed, the most important thing remains: ensuring they function perfectly. Let's get started. Step 6. Inspection and testing. Before any bullet can be packaged and shipped, it must undergo rigorous quality control tests. Operators, assisted by specialized machines, inspect each cartridge for weight, dimensions, powder level, sealing, and projectile alignment. These checks use advanced technologies, laser sensors, precision scales, and high-speed cameras to detect the slightest deviations. To confirm real-world performance, a random sample from each batch is taken to a test firing range. There, the bullets are fired under controlled conditions to verify velocity, trajectory, impact, and consistency. If any sample shows a defect, the entire batch is halted until the issue is found and corrected. Safety comes first. Only bullets that pass all tests continue forward. The rest are rejected or recycled. And now that the best have been selected, it's time to pack them and prepare them for their final destination. Let's take a look. Step 7. Packaging and distribution. All bullets that pass inspection move to the packaging and shipping phase. Finished ammunition travels along conveyor belts to automated packing stations, where they're sorted by caliber, type, and purpose. They're packed into durable boxes, hermetically sealed and labeled with key data: batch number, bullet type, and manufacturing date. In one of these plants, over 5,000 bullets per minute can be produced and packed. A staggering pace that highlights the intensity of this industry. Once packed, boxes are grouped onto pallets and sent to logistics centers, from which they're distributed to military forces, police departments, gun manufacturers, specialty stores, and shooting clubs worldwide. The entire distribution process follows strict security protocols with video surveillance, digital tracking, and authorized personnel only. From a sheet of metal to a ready-to-fire bullet, This process combines engineering, precision, and great responsibility. In speaking of responsibility, it's important to remember that a firearm is not a toy. It's a powerful tool designed for specific purposes, one that must be used with the utmost care and respect. Having access to a bullet means having access to a fragment of that power, and understanding how it's made helps us appreciate the responsibility it carries. To wrap up, tell us, did you imagine all that goes into making a bullet? Have you ever fired a gun before? Share your answer in the comments. If you enjoyed this documentary, don't forget to like the video, subscribe, and turn on the bell so you don't miss any of our upcoming content. But don't go just yet. There's more to come. The next part of this video will be just as fascinating, so stay with us until the end.
A small piece of uranium, the size of a grape, can produce enough energy to power an entire neighborhood for an entire year. But how can such a tiny amount pack such a powerful punch? To find out, let's dive into the factories responsible for producing and processing the world's most dangerous metal and explore its incredible journey together. The history of enriched uranium is closely linked to the birth of nuclear energy. In 1896, French physicist Henri Becquerel discovered radioactivity by observing that uranium spontaneously emitted radiation. This discovery inspired Marie and Pierre Curie, who isolated elements such as radium and polonium. In 1932, James Chadwick discovered the neutron, a fundamental particle for nuclear fission. Then, in 1938, Otto Hahn and Fritz Strassmann, with the collaboration of Lise Meitner and Otto Frisch, demonstrated that a uranium atom could split when struck by neutrons, releasing a colossal amount of energy. Enriched uranium, essential for controlled fission, represented a major technological challenge. Natural uranium contains approximately 99.3% uranium-238, which is difficult to split, and only 0.7% uranium-235, which is perfectly suited to fission. Increasing the proportion of uranium-235, a process called enrichment, proved essential for both nuclear reactors and atomic weapons. During World War II, as part of the Manhattan Project, scientists developed the first enrichment methods. Gaseous diffusion used porous membranes to separate uranium hexafluoride gas, while electromagnetic separation used magnetic fields to deflect the isotopes. These processes were slow and energy-intensive. In the 1950s, gas centrifuges revolutionized production. These machines, spinning at breakneck speeds, separated isotopes by mass in a much more efficient and compact manner. Their design was so strategic that their plans were classified as a state secret. In 1951, the experimental Berthaer Reactor 1 reactor at IDEO used enriched uranium to generate electricity for the first time, lighting 4 light bulbs. 3 years later, in 1954, the Obninsk power plant in the Soviet Union became the first to connect nuclear power to the electricity grid using uranium enriched to 5%. Today, enriched uranium fuels reactors that generate approximately 10% of the world's electricity. But how can this element produce so much energy? The journey begins in uranium mines, located in remote areas such as the Australian desert, the steppes of Kazakhstan, or the rock formations of Canada, which together provide nearly 70% of the world's production. Uranium is present in minerals such as peach or uranite, often in low concentrations, between 0.1% and 2%. Operations can be open pit, where huge excavators remove the earth, or underground, with galleries extending several hundred meters down. In some cases, in situ leaching is used. Chemical solutions, such as sulfuric acid or carbonates, are injected into the deep layers to dissolve the uranium, which is then pumped to the surface. The extracted or is transported to processing plants, where it is ground into a fine powder, similar to coarse sand, to facilitate separation. It is then mixed with acids or bases in large steel tanks. This process isolates uranium from other elements, such as iron or quartz. The resulting product is a bright yellow powder called yellow cake, or uranium oxide, containing approximately 80% pure uranium. This material, which is weakly radioactive but toxic if inhaled, requires protective equipment, masks, and sophisticated ventilation system. A single ton of this yellow cake can provide as much energy as several million tons of coal. It is then shipped to conversion plants, where it is transformed into uranium hexafluoride, a gaseous compound at moderate temperatures, ideal for enrichment. The process begins by purifying the yellow cake to remove impurities such as sulfur, magnesium, and other metals. This step takes place in corrosion-resistant stainless steel tanks. The purified uranium is mixed with hydrofluoric acid and then heated in sealed reactors. It transforms into uranium hexafluoride, a volatile compound that transforms from solid to gaseous at around 56 degrees Celsius. It is then stored in cylindrical steel containers specially designed to withstand its corrosive nature as it reacts violently with water. Conversion plants are governed by strict safety standards and feature advanced ventilation systems and highly sensitive leak detectors. At room temperature, uranium hexafluoride can crystallize into a fine green powder nicknamed nuclear snow because of its texture and color, although handling requires specialized equipment. The next step, enrichment, aims to increase the proportion of uranium-235 to about 5% for civilian use. Gas centrifuges, a true marvel of engineering, perform this task. Made from special steels or carbon fiber composites, they rotate at over 50,000 revolutions per minute in vacuum chambers. Uranium hexafluoride gas is injected into them. Centrifugal force separates the isotopes, with the lightest, uranium-235, concentrating in the center, while the heaviest, uranium-238, is expelled to the outside. The uranium-235 enriched gas is then collected separately. The centrifuges operate in cascades, that is, in a series of hundreds or thousands of interconnected machines. Each refines the mixture a little further until it reaches the desired level of enrichment. These installations are surprisingly quiet. Only the slightest vibrations due to rotation are perceptible. The slightest imbalance, even a few milligrams, could damage them, hence the constant monitoring by sensors and automatic systems. A modern centrifuge can process several tons of uranium gas each year. The most recent complexes, particularly in Europe, house cascades capable of operating continuously for decades. The enriched gas is then converted back into solid uranium oxide through controlled chemical reactions. This new oxide, ground into a fine powder, is pressed into molds to form small cylindrical pellets about 1 centimeter in diameter and weighing 7 grams each. They are then fired in ovens at about 1,400 degrees Celsius to produce a very dense material capable of withstanding the heat and radioactivity of the reactor core. Each pellet undergoes rigorous quality controls. X-rays detect microcracks, lasers verify dimensions, and chemical analyses ensure the absence of impurities such as boron or carbon. A single one of these pellets releases as much energy as a ton of coal. They are inserted into long tubes made of zirconium, a silvery metal that is corrosion-resistant and transparent to neutrons, a property essential for fission. Each fuel rod, approximately 4 meters long, contains nearly 400 pellets stacked with millimeter precision. The rods are assembled into clusters, called fuel assemblies, comprising several dozen rods fixed in metal structures made of robust alloys, such as stainless steel or cercolois. A single assembly weighs approximately 500 kilograms and requires more than 100,000 welds, each verified by ultrasound. The internal grids are designed with precise geometric patterns to optimize the flow of neutrons and coolant. Before shipment, these assemblies undergo extensive testing, including ultra-precise weighing and vibration, simulating reactor conditions, ultrasonic inspections, chemical analyses, and pressure tests. A single assembly can produce enough electricity to power 100 homes for a year. At this stage, the radioactivity remains low. Technicians can handle them with simple gloves and filter masks. In the nuclear power plant, the assemblies are placed in the reactor core, where fission is activated. A typical reactor contains about 480 assemblies, or nearly 5,760 fuel rods, enough to power an entire small city. During fission, the atoms of uranium-235 split under the impact of neutrons, releasing heat and new neutrons that sustain the chain reaction. The energy released by a single atom is millions of times greater than that released by a burned carbon atom. To control this reaction, regulation rods made of boron or cadmium absorb some of the neutrons. The reactor core is protected by thick, 2-meter-high reinforced concrete walls designed to withstand earthquakes, floods, or even a plane crash. Automated systems continuously monitor temperature, pressure, and neutron flux, immediately shutting down the reactor at the slightest abnormal signal. The heat from fission is used to convert water into high-pressure steam, which drives huge turbines spinning at about 1,800 revolutions per minute. These turbines are connected to a generator that converts the motion into electricity. A single reactor can produce over 750 megawatts, enough to power 500,000 homes, the equivalent of a large city. Unlike coal-fired power plants, nuclear power plants emit almost no carbon dioxide, yet they provide continuous energy production. This characteristic makes them an essential tool for the global energy transition. After approximately a year of operation, the fuel rods are removed, their energy having been almost completely released. However, they remain extremely hot and radioactive. They are therefore manipulated remotely by robotic arms, then immersed in cooling pools located within the power plants themselves. These pools, approximately 8 meters deep and filled with ultra-pure water, serve as both a shield and a cooling system. The water is constantly filtered and monitored to detect the slightest variation in temperature or radioactivity. The rods remain in the water for about 10 years, allowing their heat and radioactivity to significantly diminish. Some power plants store more than 700,000 spent rods, an impressive volume, but one that would fit in a medium-sized warehouse. Fascinating fact, these pools sometimes emit a faint blue glow, known as the Cherenkov effect, caused by particles moving faster than light in the water, a spectacular but harmless phenomenon. After several years, the cooled fuel is transferred into dry steel and concrete containers capable of preserving it for centuries. These containers, stored in secure locations, are resistant to shocks, weather, and natural disasters. Long-term nuclear waste management remains a major research topic. Scientists are working on deep geological repositories located more than 500 meters underground in stable rock formations, such as granite or salt, to permanently isolate waste. Projects such as Yucca Mountain in the United States or Onkalo in Finland are designed to remain safe for at least 10 millennia. Nuclear energy thus remains one of the most promising solutions for a sustainable future. Despite the prejudices, this technology now meets very strict safety standards and produces little waste compared to other industries. Moreover, it provides continuous electricity with almost no carbon emissions, making it a crucial ally in the fight against climate change. With continued investment in research and development, nuclear energy could continue to light our world in a clean, safe, and reliable way. And that's how enriched uranium is made. What do you think? Share your thoughts in the comments. If you like this documentary, don't forget to like, subscribe, and hit the bell to never miss any of our content.